So now, you don't make just core shell structures. You want the core shell structures. I say, okay, well, how many drops do you want inside of them? And you tell me you want 5. I say, well, what size do you want? Not only can you control the number, but you can control the size very easily because each flow is perfectly well controlled. So Yang Yin showed me that. I said, well, that's very nice, but let's do something really different. And so look, here's an emulsion generator. Here's an emulsion generator. What about here? You can align them very easily, so let's just add a third emulsion generator. And that works perfectly. So now you make Russian doll emulsions. You make drops inside of drops inside of drops with really perfect control. Of course, you look at that and you say, who would ever do something like that except a stupid academic? Why would you care about this? So I told Yang Yin, we have to show you that you care about it. So we made a structure. This is a structure where this is an emulsion, a water and oil emulsion. It's all in an oil continuous emulsion, but this emulsion here has some very delicate peptides inside it. We want to protect it because outside in this emulsion there's a surfactants, all kinds of other things that you need in an emulsion. And so we want to protect them. So what we did was we used this ability to make these structures, and here we put a hydrogel. And that hydrogel protects this inner emulsion perfectly. But this particular hydrogel is thermoresponsive. It responds to temperature. It responds to temperature by shrinking, by trying to collapse. And so look what happens if we just gently heat it up. It tries to collapse. And it tries to collapse. It tries to squeeze the inside, but it can't. It's incompressible. So instead it tears itself apart and releases it. So what have I just showed you? I've showed you a structure that really encapsulates very well, but also that releases on command. And if you think about trying to make structures that encapsulate and release, your problem is never that you can't make something that very robustly encapsulates things. The problem is if you do, it's very hard to release. And it's also very easy to make something that releases easily, but it's very hard to make it robust in its encapsulation. By controlling all these fluids now, your imagination can run wild and you can make these structures that both robustly encapsulate and controllably release materials. And this is just an example. So, okay, I can go on and show you all kinds of cool things that we did, but I think already it's sort of interesting. And we had to ask, could we make this in sufficient quantities to be interesting? So, I always tell the story. One day, I thought about this, and, well, Anderson was there. He was such a great student. He's a great professor now. He could make these devices in half an hour. I said, well, Anderson, we have to test these things. Could you please make 2 devices, and we'll test them. We'll see whether they're uniform. We'll compare the drops, the emulsions, the double emulsions made from one to the other. We'll see if they're the same. So he went away. An hour later, right, half an hour for each device. An hour later, he came back with 2 devices, and we tested. And, he's a great student. They were perfect. You couldn't distinguish them. I said, well, okay, that's easy, Anderson. Now, here's a little bit more challenge. Make 10 devices, and let's compare them. And he looked at me, not such a happy look on his face. 10 devices, 5 hours work. Okay, came away, went away. The next day, 5 hours, a little time to eat, time to sleep, come back. The next day, brought the 10 devices. Again, we tested them, and they were perfect. You couldn't distinguish them. So then I told him, okay, Anderson, that's great, but now we have to make enough materials to do some experiments. Please make 10,000 devices. And he looked at me, and he smiled, this great smile on his face. He got up, he walked out of my office, and he graduated. He had much better things in his life to do. That's just not the way to do it, right? It doesn't scale. So how do you scale something like this? Well, you scale something like this by going across the street where George Whitesides works and say, George, please teach us about soft lithography. Because with soft lithography, you make a device, I won't tell you the details, but the important thing, you make a device by using a mask. And you make that very carefully with a CAD program. You make it really designed. But then if you want to make 2 devices, it's copy-paste, right? Copy-paste, 2 devices. You want 4 devices, copy-paste, copy-paste. 8 devices, copy-paste, copy-paste. You can see the scaling is very different. So if you can make devices like this, now you can scale it. So we started to try to do this. So here's an example. This is just one device where we're changing the flow rate. This is an emulsion generator. It looks just like Liang-Yin's, right? 1, 2, makes a double emulsion. Changing the flow rates, you can change the number of drops. You can make a triple emulsion, 1, 2, 3. If you look carefully, you see it really is a triple. It's actually very interesting physics, as you always get only one drop at a time. There's interesting physics as to why you do this. But the person who was doing this, Adam Abate, a postdoc at the time, said, well, Liang-Yin already made triple layers. I got to do something much better. So he made a quintuple emulsion.